Right. Thank you for the introduction, Phil. Before beginning, a few words on my courses. This guy is the only one working here. It's He's doing the PhD. He's actually busy writing up, so he should have been here, but I convinced him that it was not such a good idea. And you'll know why after the talk, actually. So I am Jean-Yves Buffier, as mentioned by Phil. So I've been working in looking at things in 3D, and among other things I'm now more and more looking at cracks in 3D. So this poor guy has done his PhD with not only one but two supervisors. So I was one, and the other one was Julien Rétoré, who's actually also working at INSA. Actually I should have started like this. I come from INSA in Lyon. I work in a material science lab, and Julien, who has done all the DVC, soft and everything, he works in a mechanical engineering lab, so the lamp. And this other guy, Arnaud, has helped us with the machining of the notches. So all this has been done during a research project called Rubik's Cube. I'll come back to that later. So just to start, I selected this plot. You all recognize the Paris curve for, this is probably too small to read, it's a 2024 T3 alloy. GADN about delta K, and my background is more experiments. So I'm quite happy with this side of the curve here, where you can measure things happily, so measuring the length of a crack at a surface, for example. And of course, usually we struggle a bit more with this side of the curve, where we need the K value. So usually what you do is, if your crack has a reasonable shape, or if your stress state is quite well known, well, you go to handbooks and you compute the K value. If you know that you have a 3D crack, then you can go to more clever formulas. Ratio and Newmans are examples. And then you have the K value, and you can plot this. And you're happy here, you're less happy here. We heard about that this morning. However, we all know, I suppose, that in many cases this computation of K is not really satisfactory. So we calculate things, but what about the real values? And reasons why the calculated values are not exactly the same that the crack is experiencing in the material is, for example, crack closure. We talked about that this morning. Short cracks also, crack tip shielding. If the crack is has a really complex shape, etc. So what we would really like to do is extract the values, measure the K values of the sample. So there are a few people who have done that. We saw some examples this morning. I picked up some local examples from Pablo and Phil, I think, was associated with this. You look at the surface, map the displacement of the crack, and from that you extract the K values. So this is 2D, that's at the surface. In the early 2000 years here, Hiroyuki Toda used the first tomography images on some aluminium sample to map the displacement field at the tip of a crack in, I think it was a 2000 series aluminium alloy. Again, at the time he was tracking the particles. Well, he was on sabbatical in Southampton, so he had time to count them. So he was pairing them and looking at the crack tip displacement field, and from that he inferred the K1, K2, K3 values, and since then he has worked a lot on that and developed more automatic and robust methods. And we've also contributed in that field. We used also X-ray tomography, but a more global approach. This time we are not counting the particles, but we are doing image correlation. So, to make it clear, this morning we heard about image correlation, which was called DIC, digital image correlation. In that case, we will make the correlation on small voxels, small elements, so I will call it DVC, digital volume correlation. So when you have a 3D image of a sample with a crack, you can compute the displacement field, and from that extract the K values. So we've worked, of course you need one sample which has some markers to be able to do the correlation. So we used nodular graphite cast iron, and the way we were doing the experiment was have a large fatig sample, grow a fatig crack, and then from this large sample extract a small one that could fit in the tomograph, and then load this sample in situ to extract the the displacement field. So there are some issues with that. One, and not the least, is what is the influence of the sample preparation. So you cut your sample from a very large one, so in terms of, for example, plasticity-induced crack closure, for example, how much of that do you lose when you go to a tiny sample? And also, those cracks were through cracks, and we were more interested in 3D cracks, really. So that was the job we gave to this poor student. Try to do something similar, but with a crack starting from a notch inside the sample, in situ. This is what I will try to describe. I'm afraid that I will only show preliminary results. That's to say that it took us nearly 2 years and a half to do all this. And then we are now nearly at the end of the PhD, but we have a few results that I will show you. But now the real fun really starts. I will also say a few words about the limits and some conclusions on what we want to do next. The material is the same. It's a nodular cast iron, so it has a ferritic matrix. Grain size is 50 micron. The size of the nodules is also 50 micron. And the samples are 1.5 by 1.5 mil. We have machined some notches in the sample, some corner notches or some surface notches here, and they have been done by this guy in Canada, Arnaud Vec, from the University of Ottawa, using a laser. So we cycle the sample in situ, so we put the machine in the tomograph here. This is the X-ray source. The trick is to get the sample as close to the source as possible, because this is a divergent beam, so you need quite a low voxel size. So in that case it was something like 15 millimeters. So the machine is there, and we cycle the sample and record the images on the other side of the CCD, which is well, not as cheap as the one we saw this morning. This one is a bit more expensive, but it turns out to be quite helpful. The way we're running the experiment is quite straightforward. You first take a reference image, which is your reference scan, as I will call it later. Actually, we take two in general to calibrate the technique, and then we cycle. And after a number of cycles, we cycle at 20 Hertz, we stop, and you take a series of images, of scans, in fact, at increasing loads, and then you start again. Sometimes we also take images while unloading, but most of the time during the loading part. So again, we cycle and so on and so on. So we're doing constant amplitude tests at 0.1 ratio, and the voxel size, the voxel is actually like the pixel for a 2D image. It's the elementary cell of the 3D image is 2.5 micron. Basically, that gives you a spatial resolution of the order of 5 micron, which is not very good, and probably not good enough to see the crack tip, the very crack tip, but we are going to get it differently. One scan lasts 45 minutes. You will see at the end of the talk that this is also an issue. So we are using digital image, or I should say digital volume correlation to get the information we want, and we are also going to use it to get the crack. Because as you know, so this is the reference image, this is the sample distorted, then you distort this image again by applying a displacement U to go back to this. And of course, your software doesn't know that there is a crack, so when you plot the residual of the correlation measurement, you get some very large values here, meaning that there are some correlation errors here, and that helps you to detect the crack. So this is how we were detecting the crack in the sample. Okay, and you can of course follow the crack growing inside the material from this visualization of the residues. So we can grow the cracks from the corners or from the surface. So those images are the images, the 3D projection, the projection on the 3D images of the correlation residuals again. So that gives you an idea where the crack front is. So we are not using the gray level image for finding the crack tip. You can see that very quickly the crack gets away from the notch because they are quite nasty notches. And of course your A value, as I showed in the first slide, goes up very quickly because this is constant amplitude cycling. And from that we will go to the displacement field and we want to extract the K values. So how do you go to the K values? Well, there are 1D methods, which are, for example, taking the COD. We heard a lot about that this morning in the first talk. You can also use the interaction integral. But here the idea is that we have richer information, if you like, in the whole plane. So we are going to use the 2D information, but in different planes. So we basically use this Williams series approach, where you have some terms here which gives you several information. You get the rigid body translations, you get rotations and T-stresses, and K1, K2 and K3. And something else we've been using is that we will calculate a crack front position by cancelling one of the components of the development here, which is the component of the so-called super-singular term, which is n equal to -1. So the way it works is you start from the displacement fields here, so mode 1, mode 2 and mode 3. Mode 1 is here, for example. And then you take your crack front, which you have derived from the first coarse DVC. Then you select one plane which is perpendicular to the crack surface and local crack front. And then in this plane, the green plane here, you will map the displacement field, excluding the crack surface and a small circle here, which is the crack tip, because there the displacements are really ill-defined, actually. So it's an iterative process. So you first start with the blue curve here, which is your first guess for the crack front from the DVC calculation. Then you split this into regularly spaced planes. On those planes you try to cancel this -1 term in the series. That gives you a new crack front, and from that new crack front you iterate again until you get convergence of the crack front. We've used, as I said, 3D image correlation at different scales. So you start with some really coarse mesh, which you then refine more and more. And I think we then went further down to 8 voxel size. That's the size of the small element that you are using to perform the DVC. And again, you can perform it at 2 different times, either between the cycles to have a coarse idea, a rough idea of where the crack is, and also for a given number of cycles between the successive loads, in order to check the case and to extract the useful information. So this is what it looks like, and unfortunately that was bad news, because when we said we want to measure the K values along the crack front, not having a larger fatig sample that we cut, then you end up with very small cracks. And those very small cracks gives you a very noisy signal in correlation. And you can see it here. It's cut within one sample. You see it's very noisy. So to help out the correlation, we resorted to mechanical regularization. That's to say, you will take a narrow zone around the crack where the correlation will give the displacement field. And in the other region here, it will just be driven by the mechanics. Now you can correlate several things. You can do first between your zero load and all the maximum load during cycling. That will give you a rough idea of where the crack is. So the yellow images of the crack I showed you were obtained like this. Then you can also do the correlation between the minimum loads at different numbers of cycles, and you will see that we believe that gives you the accumulated plastic strain. You can also do it for a given number of cycles between the minimum and maximum load. That will give you delta K. And if you're using the different values for one cycle, that should give you the K opening. This I'm not going to talk about. It's still to be done. So, as I said, preliminary results. He's done a lot. We've been using synchrotron tomography, lab CT, but he's still in the process of processing the data and getting the results. So we'll show you one sample, which we call LB1, and the last number of cycles we got, which is 160,000 cycles. So he's done all that, which needs to be processed. Okay, crack opening maps during cycling. So we start at 0 and then down to 160,000. This is the mesh that we have used. I don't know if it's visible from the bottom of the room, but it's a refined mesh. Here it's quite coarse. On those surfaces we apply the displacement which we get from the correlation at the coarse level, so real conditions of loading, of displacement at least, and we get the displacement fields. So the correlation we get between the minimum load and the maximum load for the 160,000 cycles are here. You can see that it's still a bit noisy. If you do it between your initial scan at the very beginning of the experiment and the minimum load at 160,000, that's to say from between this point and this point here, you get a much nicer signal. But because you see here, the difference is between 6 and -6 voxels, and here it's less than a voxel, basically. So this signal is noisy. It's because at the stage where you are, your crack opened much less than here, of course. And this is the same thing, but seen along the stress axis. And again, you see that this signal is less noisy, but this we believe it's because we accumulate plastic strain in the sample. And the amount of crack opening during one cycle is only given by this signal here. So you can still use this data to see what it gives. So you use this correlation to try to find out the crack front. So the blue line is your first guess. Then you go up there and you see it quickly converges. And this is the crack size that I'm showing as a function of the angle along the crack front. So 0 means at the surface, 180 is also at the surface, and 90 is in the bulk. You see that we get a crack which is small. It's 150 microns, more or less. So it's a small crack. We get values which are not really reasonable. It's almost 0 for K2 and K3. But for K1, if you do it like this, you find something like 70, which is, of course, physically meaningless. But that comes from the fact that we have taken all this plastic deformation that we have taken into account, that we have introduced in the material, something very similar to what Professor Novel was showing this morning. Okay, so now we want to do it but between the minimum and the maximum load at a given number of cycles. So again, the crack front determination. So you start from the first guess, which is there, and then it takes more steps. It takes 7 steps to stabilize, and there you find your new crack front, which is there. And from that, you can now compute the values of K during one loading. So from minimum load to maximum load, this is the crack size between 0 and 180 degrees. So this is the bulk value, the two surfaces value. You see, it's quite different. And now, the value we got for K1 here is, well, somewhere between 7 and 8. So if you do the analytical calculation, assuming, for example, the blue curve that I showed before, you get 7.3, which is not too bad. So that gives us the right order of magnitude, at least. What is the meaning of the variation of K2 and K3? Well, if you have some clever ideas, I'll be happy to hear them. It's probably noise, maybe not. There are funny effects here at the surface, but you can see that, okay, it's more or less centered to 0, but maybe these values are meaningful. I don't know yet. Okay, so that's all for the results. There are some problems, and I want to underline two problems. One is that we are using lab city, and lab city are less stable than synchrotron sources, and you have thermal issues. That's to say, one scan lasts 3/4 of an hour, so it takes hours to scan one sample. So during the time, your X-ray source will drift a little bit, and that gives you, so those points here are the strain you get by just setting one sample in the tomograph and not doing anything. You just record some scans after, well, some minutes, hundreds of minutes. And you see that you have apparent strain. It's just because the position of your source is changing, so the magnification on the image is changing. And if you pay attention to the scale, this is of the order of 10 to the minus 3, which is more or less the order of your elastic limit divided by the elastic modulus. So that's exactly the kind of strain you're after. So if you plot the load here as a function of strain, your raw signal is there, the thermal signal is there, so once you subtract this one from this, you get this one, which is the really true curve. So you have to be careful. So now our source is cooled, but it took us a while to realize that, so there are some references. Another issue is, don't forget that those are reconstructed images, they are not just images taken from a cheap CCD camera. So they have defects. I don't know if you can see them from the room, but what they call, Phil knows them very well, ring artifacts. And those can fool the correlation software. So you can take those ring artifacts from some defects in the material. And you see here, this is a very bad example. The software has thought that the crack front was there, which is obviously the center of rotation of the sample. So it's been fooled by this. So the image quality is quite essential, of course. Okay, it's time to conclude. So in summary, the aim of the talk was to try to convince you that it's possible to some extent to extract 3D displacement field at the tip of fatigue crack. You need a material with a marker. In that case, we've used nodular cast iron, but you could have other ideas. Although we couldn't see the crack tip with the poor resolution we had, we managed to get an idea from correlation. And we extracted the K1, K2, K3 values. And also we had to add some regularization to the correlation, because those are really small cracks. So what needs to be done? Well, Joel has to work harder until September and process all the data that we've got, because it really took a lot of time to do all that. Maybe try other materials. Could be an idea to try to couple this with what Phil has been doing, for example, or Pablo, to map the displacement fields or the stress field at the tip of a crack. Have a look at overloads, etc. And I think that's all.